So another extension 1 area of calculus you guys learned about is how to integrate sine squared x and cos squared x. So the way we integrate them is it comes from the cosine double angle formula. So remember that cos 2x is equal to 2 cos squared x minus 1, and it can also be written as 1 minus 2 sine squared x as well. So using these results here, we can actually rearrange them so that we can say cos squared x. So just make cos squared x and sine squared x as the subject, and using this, you can actually integrate this. So when you integrate sine squared or cos squared, always remember to just change it into this form, because we can integrate these forms much easily than when it just integrated cos squared x or sine squared x. Thankfully for you guys, these results are on the reference sheet, so don't stress about if you forget them, but still a good idea to know these formulas by memory. For us, when I did the HSC back in 2018, we didn't have these formulas on the reference sheet. We had a different reference sheet, so we had to know these by heart. But for you guys, if you do forget, it is on your reference sheet. But yeah, still a good idea to sort of know these. You can just quote them, because it will be more efficient that way. Okay, so in extension 1, you also learned how to do volumes of solids of revolution. So basically, a solid of revolution is the 3-dimensional solid that you get when you sort of rotate the area bounded by a curve around a particular axis. And I really love this topic here because I love the shapes that you could get with solids of revolutions. They're super cool. The idea of just rotating an area around an axis and getting a 3D shape and finding the volume of that, that's pretty cool. So the way we actually find the volume of a solid of revolution is we basically slice the volume up into a bunch of thin discs or cylinders, and then basically add those slices up to get our volume. So for example, if you have this like sort of area here that you're rotating around the x-axis, when we slice, basically the radius of the slice that you get is going to be the y, whatever the y value is of that coordinate. So no matter when you move along the disk, when we or the function, when we slice, the radius of that slice is going to be y. So therefore, the area of the circle is actually going to be pi y squared. And basically, when we sum up all the disks from a to b, we actually just get an integral from a to b of pi y squared dx, because we're slicing with respect to because we're slicing, our widths of these slices are going to be delta x, a small change in x. So when we basically sum up all of these disks, we get the integral from from a to b of pi y squared dx. So that's where the formula you learned comes from. Just make sure you sort of understand that it's because the radius of this disk is whatever the y value is, and the area of the circle, we know the area of circle is pi r squared, so the area of that circle is pi y squared, because y is the radius, and therefore when we integrate these super thin disks, we will get the integral from a to b of pi y squared. And the same thing works with when you're rotating around the y-axis as well. The difference is we're slicing, our discs that we slice will look like that. So this is just a point on the graph. And instead of having the radius be the y-axis, the y value, this time the radius is actually going to whatever the x value is. So this time, when we find the area of that circle, it will be pi x squared instead. And if this is a and this is b, we'll be integrating from a to b. And this is a small change in y, it's like delta y. So therefore, it will be dy. So yeah, basically, if you're rotating around the x-axis, this is your formula to find the volume. And if you're rotating around the y-axis, this is your formula to find the volume. So don't forget the pi, it's important. If you don't put the y, you're going to not get the right answer if you don't put a pi. Also, because this is dx and this is dy, make sure whatever you have here will be in terms of y, and this is in terms of x. So you're going to have to convert y squared in terms of x before you can actually integrate, because of the dx and the dy. So here's just a question we can do. We want to find the volume of the solid formed when the area bounded by the parabola y equals 9 minus x squared, and the x-axis is rotated around for part A, the x-axis, and for part B, the y-axis. So I reckon for the purpose of making sure we get through more content, I'm just going to do part B, but you guys can attempt part A on your own if you want an extra question to do. So always draw a diagram. We have 9 minus y equals 9 minus x squared, so that's going to be a concave down parabola. And it will actually, when y equals 0, 0 equals 9 minus x squared equals 9, so it will be plus minus 3, so we know that it has x-intercepts at 3 and negative 3. So the area bounded by this parabola and the x-axis, so this area, for part B, we are rotating it around the y-axis. So it will sort of look like this shape, where it's a dome, sort of a shape. And when we slice, we know that this point here, the radius of the slice is going to be x. So therefore, my volume here is going to be pi integral from, I'm going to be slicing from the bottom where y is equal to 0 all the way up to the top where y equals 9. So my integral from 0 to 9 of x squared dy. Now here's the thing, this is dy, so I need to make sure that this is in terms of y. We know that y is equal to 9 minus x squared, so we can say that x squared is simply going to be 9 minus y. If I rearrange that equation, I can say x squared equals 9 minus y. So this is the pi integral from 0 to 9 of 9 minus y dy. So when I integrate this, this will be pi 9y minus y squared over 2 from 0 to 9. And when I plug in the numbers there, I'll get 9 times 9, which is 81, minus 9 squared, which is 81 over 2, minus 0 plus 0. So this will give me 81 over 2 pi cubic units, like so. Remember, it's a volume, so answer with your units in cubic terms. It's cubic units. So that's what the volume is of this shape that we get when we rotate the area bounded by that parabola around the y-axis.